In this lesson, we're going to look at how we can apply right triangle trigonometry, or if you prefer, SOHCAHTOA trigonometry, to applied situations or story problems rather than ones where you are simply given a triangle and asked to solve for a missing angle or a missing side. So I give a summary of the steps I'm going to be following here. They're pretty rudimentary. The first step is I'm going to sketch the situation described to scale as best as possible. It doesn't have to be perfectly to scale. It helps you to understand when you look at your triangle, if you've drawn it to scale, that your answer makes sense or not. So you can look at your answer and say, wow, this length doesn't make any sense based on this picture. Whereas if your drawing is not to scale, then you can't look at your picture and gain any information about the reasonableness of your answers. So that's what I mean by trying to draw things to scale. And what this means is if you have two lengths, they should be proportionate to one another. So if you have a 10-foot length and a 5-foot length, the 10-foot length should try to look twice as long as the 5-foot length. And as best as you can, make angles look correct as well without going to the extent of getting out a protractor and measuring them. So second, is we're going to look for a right triangle where you can solve for information that will let you answer your problems. So since there's no picture given, you're going to have to find the right triangle in the picture. Some of these will be easier, some of these will be a little bit trickier. And then finally, last is you use your SOHCAHTOA trigonometry, sine or cosine or tangent, to find that needed information, and then you answer the question. And you have to be careful because sometimes the SOHCAHTOA answer you get from is not the immediate answer to the question. I have 3 examples laid out for this lesson. So here's the first. This says, at a time when the angle of elevation of the sun is 51 degrees, a tree casts an 8-foot long shadow on level flat ground. How tall is this tree? So first, before I draw my picture, I should explain this idea, angle of elevation. So angle of elevation is simply, if you imagine a horizontal line, if you're looking at something up in the sky or above you, the amount of degrees you have to turn up from horizontal is called an angle of elevation. And it's always in reference to a horizontal line. You will also sometimes see story problems where you have something called an angle of depression, which is the same idea, but it's now how many degrees you need to go down from a horizontal line. It's always using a horizontal line as a reference. So this would be an angle of depression. So you're elevating your line of sight or you're depressing your line of sight. So let's see if we can sketch the situation here. So we have at a time when the angle of elevation of the sun is 51 degrees. So that means if you have a horizontal line, you have to look up 51 degrees to see the sun. A tree casts an 8-foot long shadow on level flat ground. How tall is this tree? So we have a tree. There's my fantastic artistic rendition of a tree. Looks like a folded up umbrella. And then we have the tree casting a shadow, and the angle of elevation of the sun, so here's my level flat ground. The angle of elevation of the sun, this angle here, is 51 degrees. So that means if we imagine where the shadow ends, so maybe the shadow looks like this along the ground, the angle that we look up to the sun, like that, is 51 degrees. Because the idea, here come the sun's rays coming down, and this tree is blocking them, so the tree is casting a shadow. And if we look back at the sun along this line of sight, there's a 51 degree angle of elevation. So this is a sketch of the situation. We know the 51 degree angle, the angle of elevation, and we know the length of the shadow is 8 feet. And since we have level flat ground here, this is going to form a right triangle. You might say, well, what if the tree is leaning? But that would still, the top point of the tree is what's going to give the top point of the shadow. So here's my right triangle. So now I'm going to use my trigonometric ratios to figure out the side that I need that will let me answer the question. If I label this triangle for trigonometry, I will have hypotenuse here across from the right angle. Then since the angle is down here, going across the angle, we'll find the adjacent side of the triangle here, and then opposite the angle, we'll find the opposite side of the triangle. So these are the three sides of my triangle. So what I need to ask is, what information do I need to know in order to answer the question, how tall is the tree? Here it's straightforward. We need this opposite length. And since we know the adjacent length, if I remember my mnemonic for the trigonometric ratios, the trigonometric ratio that connects opposite with adjacent is tangent. There I have the TOA. So I can write tangent, then I write the angle, 51 degrees, is opposite over adjacent. Opposite is unknown to me, adjacent is 8. So I need to ask my calculator what tangent 51 is. Let me get my calculator out. There it is. It is in degree mode. Good thing to check. So tangent 51 is 1.235. I always put a lot of the digits here to minimize intermediate rounding inaccuracies. So to get opposite, I just have to multiply both sides of this equation by 8. Those divide away, and the opposite is 9.9. And what's my units for these lengths? It's feet. 9.9 feet. And in this case, this answers the question. The opposite side is the length, the height of the tree. So the tree is 9.9 feet tall, not a towering oak. So that's my first example. Let's look at one where the triangle is not directly on the ground. It adds a level of complication to things. This reads, Julie, whose eyes are 4 feet off the ground, looks up at the top of a 20-foot tall pole. How many degrees is she looking upward if she is standing 15 feet from this pole? So again, I'm going to start with the sketch. We have Julie. I like to put my things that are looking on the left for some reason. So Julie, who's only 4 feet tall, or at least her eyes are 4 feet off the ground. So she's over here. Here's my stick figure girl. Give her some arms. So her eyes are 4 feet off the ground. So that's 4 right there. And she's standing 15 feet, so that's about 4 fours. So she's 15 feet from this pole, and the pole is 20 feet tall, so it's five of her. So 1, 2, 3, 4, 5, something like that. So it's this really tall pole, which is 20 feet tall. So this is our situation. Julie's 4 feet tall, or her eyes are 4 feet off the ground. She's a young girl. She's 15 feet from this pole. Here's my pole. The pole is 20 feet tall. How many degrees is she looking upward if she's standing 15 feet from the pole? So this is another angle of elevation. When I talk about degrees looking upward, it's going to be, we have a horizontal line going like this from her eyes, and then she's looking at the top of the pole, and I want to know this angle here, A. How many degrees does she have to look upwards? So this is similar to the last question. There's a couple of differences. One is the unknown is different. In the previous question, I knew the angle and I wanted to figure out the height of the tree. Here, the unknown is the angle itself. So there's going to be some inverse trigonometric ideas coming into play. But the other key difference is the right triangle here is floating off of the ground, which means when you label hypotenuse opposite adjacent, you have to think carefully about what some of these lengths are, because the triangle is not directly on the ground. So when I label this, this of course is hypotenuse here. It's across from the right angle. My angle is here, so this is adjacent. And across from the angle, we'll find the opposite side. So I know the adjacent here is this full 15 feet from where Julie is standing to the pole. But the opposite here isn't the full 20. The pole goes all the way to the ground, like so. And the triangle doesn't. The triangle stops right here, and it stops this 4 feet from the ground. So that means this opposite length here is 16 feet. And I have to be careful about that, because the triangle's off the ground. I don't have the full length of the pole in this triangle. I only have some of the length of the pole in the triangle. So I need to figure out how many degrees she's looking upwards. So I can figure that out now, because I know two sides of this right triangle. I know the opposite is 16, and I know the adjacent is 15, and the trigonometric ratio, again, that connects opposite to adjacent, is tangent. So I will have tangent, my unknown angle A, is opposite over adjacent, 16 over 15. Taking my calculator out, 16 divided by 15 is 1.06, and then the 6 repeats. And remember, to get the A by itself, because that's what I want to know, is the angle, I have to inverse away this tangent. So it's kind of like, it looks a lot like division, but it's doing an inverse. So I'm going to have inverse tangent of this number here. And then that's the number I want to do. So I'll just do answer. This refers to the previous answer. And I get 46.8 degrees. It's an angle. All our angles in geometry are going to be in degrees. And then I just have to be careful, is that what the question is asking me to figure out? How many degrees is she looking upwards? Is she standing 15 feet from the pole? So yes, that is the angle I want. So that answers the question. She's looking 46.8 degrees upward. One last example. An isosceles triangle has two sides of length 8. One of the base angles of the triangle measures 70 degrees. How long is the altitude drawn to the base of this triangle? So there's some geometric language in here. Altitude, base, base angles, isosceles. We have to remember what all these terms mean before we can set this problem up correctly. So, quick review. When you have an isosceles triangle, you have at least two sides that are the same. The remaining side is called the base, because we typically draw an isosceles triangle with this side on the bottom. And then these angles here that touch the base are referred to as the base angles of the isosceles triangle. It's a special term that's used just for isosceles triangle, the fact that this has base angles. The base angles theorem reminds us that these angles are the same. Finally, an altitude drawn to the base, altitudes make right angles, so we're going to have a altitude like this. This is an altitude. Altitudes always make right angles. So this is where my right triangle is going to come in so that I can do my trigonometry. So let's draw this specific situation. We have an isosceles triangle with two sides of length 8. One of the base angles measures 70 degrees. So the other one's also 70, because as I mentioned, the base angles have to be the same. So this triangle looks kind of like a tall, skinny triangle. Something like that. These are both length 8. And then the reason it's tall and skinny is because the base angles are both 70. So it's a pretty large angle. The question is, how long is the altitude drawn to the base of the triangle? So there is the altitude drawn to the base. That's the base. And there's my right angle. I know that's a right angle because it's an altitude. And I want to know how long this is. So here's a right triangle. Not the entire triangle in this case, but just half of it. So if I set this right triangle up for trig, I'll do the one on the right since that's where I put my right angle mark. This is the hypotenuse. Here's my angle. So swinging across here, this is the adjacent side. and over here is the opposite. So now I need to ask, what do I need to know to answer the question? How long is the altitude drawn to the base? Well, the altitude is this length, so I need to figure out what the opposite is. And the one that I know is the hypotenuse. This is what I need to know. What's opposite? Hypotenuse is the one that I know. So if I think about my mnemonic again, SOHCAHTOA, the trigonometric ratio that connects opposite with hypotenuse is sine. So I will write sine, my angle is 70, is opposite my unknown over my hypotenuse of 8. Again, now I'm doing calculator work. Sine 70 is 9397 to the nearest, what is that, 4 digits, 10,000th, I guess. 9397 over 8. And then to get the opposite, I simply multiply both sides by 8. These divide away, and I'm left with the opposite is 7.52. And I don't believe any units were given for this length. No, it's just length 8. So, does this answer the question? It does. How long is the altitude? And that's the answer. So that completes this question, and we've answered this question. One note here is another question I may have asked. Instead of how long is the altitude, I could have said, how long is this base? That would have been more challenging because it wouldn't have been immediately obvious where the right triangle was. The altitude led me to drawing a right triangle, but if I had simply asked how long is the base, it might have been a little bit perplexing to have this information and go, okay, how do I figure this out? There's no right triangle. And you would have to recall, oh, if I put in a right angle here, I could figure out what this piece is here. And then because of the symmetry of isosceles triangles, however long this adjacent ends up being, which we could have gotten with cosine, I have to double that length, and that will tell me how long the base is. So you have to be alert to the relationship between the answer you get from your right triangle and how that relates to the question that's actually asked in the question. Make sure you go back after you've gotten this opposite or adjacent or hypotenuse or whatever, or maybe an angle, and ask yourself, does that answer the question that's being asked?